Hello, welcome to this video on distributions of order statistics. So, what are order statistics? Suppose you have a random sample, capital X1, capital X2, capital Xn, uh, of size n from some distribution, right? And suppose you have a realization of this random sample that is set of observed values, simple X1, simple X2 up to simple Xn. Then, if you put these observed values from smallest to largest, put in the ascending order and select the first observation, that is the minimum. Right? So from that single sample, we have one value, the minimum value from that sample. Suppose you take another random sample, simple x1, simple x2 up to simple xn from the same distribution and put them in the ascending order and then find out the first value. That is the minimum. So now you have two possible values for the minimum if you take a random sample of size n from this particular distribution. So like that, if you do it again and again and again, taking the same samples of the same size from the same population or same distribution, and then from each sample finding the minimum value, right? So from one sample, you have one minimum value. And suppose you do this again and again and again about 10,000 times, and therefore you have 10,000 possible values for the minimum of a random sample coming of size n coming from that distribution. Right. So if you now draw the histogram of these 10,000 values, then you will get certain shape, and that is the shape of the distribution of the minimum of the sample of size n from this particular distribution. So these 10,000 values are possible values of a certain statistic, certain random variable, which is a function of capital X1 up to capital Xn. So what is that statistic? That statistic is the minimum of the sample of size n when you are taking a sample from that particular distribution. So that is called the first order statistic. First order statistic. And you can do the same thing, for example, for the second, right? So instead of observing the first or the minimum value, you can keep on observing the second minimum value. From each sample, you will have one second minimum value. So if you do it again and again and again, you will have large number of possible values for the second minimum value. So that can be considered as set of possible values for the second order statistic. So that is a different statistic. It's again a function of x1, x2 up to xn. So like that, we can talk about first order statistic, second order statistic, third order statistic, and so on up to nth order statistic. So some books, so some authors denote these new random variables by writing, say, x within bracket 1, x within bracket 2, x within bracket 3, and so on, x within bracket 10. So this is the notation for the first order statistic when you consider this random sample. This is a random sample, x1 up to xn. And these are usually here we are assuming that they are IID, independent and identically distributed. So that means x1, x2 up to xn are independent. They have the same distribution. But this is some function of x1 up to xn. So that is actually the x1 here. We denote by x within bracket 1. That is the minimum of x1, x2 up to xn. Right. And in particular, if you look at this one, xn within bracket, that is a different random variable. It's a function of, again, x1 up to xn. That is the maximum of x1, x2 up to xn. Right? And similarly, you can say x2 here will be the second minimum. Right? So each of these are functions of these observable random variables. Therefore, this is a statistic, this is a statistic, and similarly, this one will be a statistic, this one will be a statistic, and so on. So those are the ones called order statistic. This is the first order statistic, second order statistic, third order statistic, and so on. Now, even if x1 up to xn are independent, these are not independent because x1 is always less than or equal to this x2 here. The first order statistic is always less than or equal to the second order statistic. So there is an order, right? Whereas x1 can be greater than or less than x2, x2 can be greater than or less than x3 and x1. So there's no order between these things. So there is an order. So therefore, these are not independent. They are not independent. Therefore, they are dependent. And also, they are not identically distributed either. Here, x1, x2 up to xn have the same distribution. But it's not like that. X1 is a completely different function of x1 up to xn. X2 is a different function. X2 is a different function. Xn is a different function. So these are different random variables. So therefore, their distributions are also different in general. Right? So therefore, they are not identically distributed either. Right? So that is one way to denote the order statistics in some books. But here, for convenience, I denote this one by y1. These are new random variable. It's a function of x1 up to xn. And I denote here this random variable by y2, this random variable by y3, and this random variable by yn. Right? So that's why I have written y1 less than or equal to y2 less than or equal to y3 up to yn, where yi are the xi arranged in order of increasing magnitudes are defined to be order statistics. Okay. Corresponding to the random sample x1 up to xn. So this is what I mentioned. Unlike the sample itself, the order statistics are not independent and they are also not clearly identically distributed. So now I'd like to show you a Shiny app to show these different distributions, right? Considering a particular distribution and considering a particular sample size. And let's see how the distribution of the first order statistic, how the distribution of the second order statistic, how the distribution of the uh, last order statistics are generated. So to show that, I will now use a certain Shiny app here I have. So let me run this Shiny app. Right. So here in the Shiny app, I have the possibility to select random samples from several distributions. I will first consider just a uniform distribution. Suppose I am taking a random sample from a uniform distribution, say, uh, between, say, 10 and 20. Right. So I'm considering my distribution from which I'm getting the sample is uniform. Right. Suppose I'm considering a sample of size 10. So my n is equal to 10. And so I will first consider the first order statistic, the minimum. Right. I'm going to generate about 1,000 values, otherwise it will take some time. So I'll generate that 1,000 values. So first of all, I'll take one sample of size 10 from this uniform distribution. Right. So generate one trial. Right. So I have here got 10 values from uniform 10, 20. So all the observations are between 10 and 20 here. I have 10 values and automatically here it has been sorted. So this is the first or the smallest value. So this is one possible value for my first order statistic. Right. So let me generate another one. Take a random sample of size 10 from the same uniform distribution. So that sample is different here. And I have now put them in the order. So this is the minimum value. So this is my second possible value for the first order statistic. Right. So when I generate one by one observations for the first order statistic, I build up a histogram of those values here. So I have now only two observations yet, right? So the histogram is like this at the moment. Is not meaningful at the moment. So let me generate another random sample of size 10. So in that sample, the minimum value is this number, 10.817. So that value is shown here with the vertical line, right? I have now generated three values, right, from three samples. So these are my three possible values for the minimum, right? So I have now three values. So like that, let me generate more and more observations by clicking on this button, right? So each time I will take a sample of size 10, put them in the increasing order and take the first value. Right? So at the moment I have about 40 values generated, 45 values, right? So these are those 45 values came from 45 samples, and at the moment this is the shape of the histogram of those 45 values. But actually, in order to, if you want to see the uh, shape of the distribution of the first order statistic approximately, you need a large number of possible values. So therefore, I will now ask the computer to generate more values up to 1,000 values automatically. Right? So auto generate up to number of 1,000 values. And at the end, I will have 1,000 possible values for the first order statistic. And I will have the histogram of those 1,000 values. So it will take some time, few seconds. Right. So it has now generated 1,000 values for X1. Right. X1, 1,000 X1 values have been generated. So these are those values. And this is the histogram of X1, the first order statistic distribution of capital X within bracket 1. So you can see that it has kind of an exponential shape. We don't know whether it's exactly exponential, but it has something like an exponential shape. Right? Why is that? Because when we are taking a sample, always these numbers in this case are going to be between 10 and 20 because I'm generating data from uniform 10-20 observation. So therefore, most of the minimum values in each sample are going to be close to 10. Right? So that's why you have the highest frequency close to 10 here. Right? Right. The minimum value will be around 13, 14, only very rarely, right? There is a larger probability that the minimum value in the sample to be close to 11, like 12, 10, 10.5, these are, right? But the minimum value being close to 20 is almost impossible when the data comes from uniform distribution. That's why we have this shape for the distribution of the first order statistic. So this is called the sampling distribution of the first order statistic. So now let me reset this. I will now look at, for example, third order statistic. Right. So I will still be generating data from the same uniform distribution. So I'll start generating. So then now here I'm considering the third minimum value, right? After putting the data in the increasing order. So this in this case, the value is 11.911, third value. Right? So if I do it again and again and again, you will see that the sample is changing, the third value is changing. So therefore, I can generate data like this. Right? So I have now 28 values. These are all possible values for the third order statistic. Right? So let me generate automatically up to 1000 values. And then we can draw the histogram and see the shape of the distribution, sampling distribution of the third order statistic. It's taking a few seconds because it has generated 1000. Yeah. Now you can see this distribution, shape of this distribution is different from the shape of the distribution of x1. Right. Now, the possible value being 10 is very, very rare. Right? Because now we are looking at the third minimum value, not the first minimum value. Right. So the third minimum value is going to be around, according to this thing, more likely to be around 12.1, 12.2, 12.3, that kind of values. Right. Uh, 10 and 11 are now less likely. And also values more than 70 are almost unlikely. Right. For x3. So that is the third order statistic. Right. Uh, let's do this for some other distribution, like say, uh, let's take a Poisson distribution discrete. So I will just consider, say, Poisson lambda equal to 4 distribution. Sample size I can change if I want, but I will just keep it as a 10. I'm taking a sample of size 10, right? So I will now again look at, now in this case, I will look at 10th order statistic, right? Maximum, right? So let's generate data. So I have now there are 10 values coming from Poisson 4 distribution, but I am interested in the last one, large one, the maximum one, 7. 7 is the value, right? So that is R equal to 10. If I say Rth order statistic, now I am uh, using R equal to 10, right? So let's do this again. So let's take another sample. Now my maximum value is 9, right? Let's take another sample. Now my maximum value is again 9. Let's take another sample. My maximum value is 6 now. So like that, if I do it again and again and again, I will generate several values. So I have generated about 23 values here. So these are the values that I got for x10, 10th order statistic, or in this case, the maximum. Right. So if I ask the computer to generate the remaining values up to 10,000 values, I will be able to see the shape of the sampling distribution of x10. Okay. So this is the distribution of x10 when the data coming from a Poisson 4 distribution and when the sample size is also 10. Right. So using this kind of distribution, simulated distributions, we can calculate some probabilities also approximately if you want. For example, what is the probability that the largest value, when you're taking as 10 observation, what is the large probability that the largest value is greater than 10? What is the probability that the largest value is less than 5? That kind of things can be obtained from simulated distributions also. Right. So that I think it is now clear to you what we mean by order statistic and what we mean by the distribution of the order statistic or sampling distribution of the order statistic. Right. Now, what we are going to look at do is to derive some formula that we can use to obtain the theoretical distribution of the first order statistic, second order statistic, third order statistic, and so on. In general, rth order statistic. Right? We want to be able to get the distribution, the CDF or PDF or PMF, depending on whether the random variable is discrete or continuous. We want to be able to get those in terms of the CDF or the PDF or PMF of x1 up to xn. Right? Suppose we know the distribution of x's, and then using that knowledge, we want to be able to derive the distribution of order statistic for a given R value. Right. So let's derive the distribution of the minimum. Suppose x1 up to xn is a random sample of size n from a continuous distribution. Here we are considering continuous distribution case only, right? But the same idea can be applied for discrete case also. But here I'm considering continuous. With cumulative distribution function, say fx, capital Fx. Let y1 be the minimum of the sample. Then find the distribution of y1. Right. So here the method I'm going to use is called the cumulative distribution function technique. That is, first find out the cumulative distribution function of y1. And then, of course, if y1 is a continuous random variable, then we can find the density function from by differentiating the cumulative distribution function of y1. Otherwise, we can get the PMF also from the CDF in case of a continuous discrete y in that case. So let's say capital F subscript y1 evaluated at some value y, that is the cumulative distribution function of y1 evaluated at y. By definition, this is the probability y1 less than or equal to simple y. It is easy to derive an expression if we write down this thing using the complement. So this is the same as 1 minus the probability y1 greater than simple y. Right. Now think of the event y1 greater than simple y. Y1 is the minimum of the sample. Minimum of the sample greater than y if and only if all the x1 up to xn, all of the random variables are greater than y. Right? So I can write down this y1 greater than, capital Y1 greater than y. In terms of x's now, it is y1 is the minimum. So minimum of x1 up to xn greater than y. But that is equivalent to, this event is equivalent to this event here. X1 is greater than y. Also x2 is greater than y, and so on. Xn is greater than y. Right? So that is the intersection of several events. Right? So the probability of that intersection. But remember, x1 up to xn are independent. Therefore, this probability of this intersection is equal to the product of the individual probability. So that is therefore this part is probability x1 greater than y, probability x2 greater than y, up to probability xn greater than y. Right. Now remember, x1 up to xn are identically distributed as well. So therefore, x1, x2, x3 all have the same distribution. So I will now write down this one as 1 minus probability x1 less than or equal to y. This one as 1 minus probability x1 less than x2 less than or equal to y, right? But that is the same as 1 minus probability x1 less than or equal to y, because x1, x2 have the same distribution. And this one I can write down probability 1 minus xn less than y, but that is the same as 1 minus probability x1 less than y, because xn and x1 have the same distribution. So therefore, suppose that the cumulative distribution function of x1, x2, x3 all are the same. Therefore, let us denote it by fx, right? So then what you have here is 1 minus fx evaluated at y. This is again 1 minus fx evaluated at y, and again 1 minus fx evaluated at y. So therefore, you get this expression 1 minus fxy to the power n. So therefore, you can now obtain the cumulative distribution function of the first order statistic, or the minimum, in terms of the CDF of x. So once you know the CDF of x, you can get the expression. We can get the density function of y1 by differentiating this expression with respect to y. Right? So when you do that, you get n to the n times 1 minus fxy to the power n minus 1. And you have to multiply that by the derivative of this function inside. So when you take the derivative of that one, you get this negative sign, and then you will get the density function of xy. Right? So this negative and this negative will cancel, become positive then. Right? So therefore, the density function of density function of y1 evaluated by y will be equal to n times 1 minus fxy to the power n minus 1, and then the density. This is coming from taking the derivative of this one. So that is the equation for the density function of y1, which is the first order statistic in terms of the CDF and the density function of x. Right. So let us look at an example, a simple example. Suppose that the lifetime of light bulbs of a certain brand is exponentially distributed with mean 100 hours. If 10 such bulbs are installed simultaneously, what is the distribution of the life of the light bulb that fails first? And what is its expected value? So from the question, it is clear that we are looking at the distribution of the first order statistic, or the distribution of the minimum, when you are considering a random sample of 10 values from an exponential distribution with mean 100. In other words, rate parameter is equal to 1 over 100. Right. So we know now the distribution of each x1 up to x10. Suppose let I denote the lifetime of the ith light bulb. I goes from 1 to 10. And let y denote the minimum in this case, because I am interested in only one. Therefore, I have not called it y1. So I have just mentioned it as y here, because I'm in this particular problem, I'm interested in only the minimum. So y is the minimum. We need to find the distribution of y, right? And expected value of y. So from the previous expression, I can write down now the density function of y should be equal to n times 1 minus fxy to the power n, 9 times the density function of x, right? So we know that the density function of x is 1 over 100 e to the power negative x over 100. That is the exponential density function with mean 100. And from that, we can get the CDF. CDF is given by this function. So I know now both functions that is required here. So when I substitute, I get this expression for the density function of the first order statistic. And you can identify this also is an exponential distribution with mean 10. Right? This implies that y, the minimum lifetime of the light bulb, is exponentially distributed with expected value 10. Right? If the observations are in hours, then 10 hours. Right? So that is the answer to this question. The distribution is exponential with mean 10. So I'd like to look at this problem by simulation also. So let me go back to the simulation and reload my application. I will now select, say, exponential distribution as my distribution. Rate I will take to be 0.01, right? 1 over 100. My sample size is 10, and the order, I'm looking at the first order statistic. Right? So let me now, as previously, generate data, few observations manually, right? So I have this value as the first value here, second, okay. So I'll do that again, few values, right? So I have generated 14 values here. These are those possible values when the data are coming from an exponential distribution with mean 100. Rate is equal to uh, 0.01. Right. So let me do this about 1,000 times to see what the distribution looks like. So this is the distribution of the first order statistic when the data come from an exponential distribution with mean 10, mean 100, and sample size is 10. Right. So this looks like an exponential distribution. So, and the mean, theoretical mean, we know it's 10. So this is the mean. So this is actually the last observation that I have got here. Right. So theoretically, it's exponential with mean 10. This is the simulation of only 1,000 numbers. If I generate about 10,000 numbers, then it will be a smooth, more smooth histogram. Right. Okay, now let's come back to the slides. So now let us look at the distribution of the maximum. Those are the two extremes, minimum and maximum. And then we will look at a general order statistic, rth order statistic. Suppose x1 up to xn is a random sample from size of size n from a continuous cumulative distribution function fx. Let yn be the maximum of x1 up to xn. Find the distribution of yn. So again, I find out the cumulative distribution function of yn evaluated at y. By definition, that is the probability that yn less than or equal to simple y. And that is the same as probability that the maximum of x1 up to xn is less than or equal to y. Right. So maximum of x1 up to xn less than or equal to y is equivalent to saying that each x1 up to xn is less than or equal to y. So therefore, this event can be written as the intersection of several events like this: x1 less than or equal to y, and x2 less than or equal to y, and so on, xn less than or equal to y. Right. Now, because x1 up to xn are independent, the probability of this intersection is equal to the product of individual probabilities. So therefore, I can write down this as probability x1 less than or equal to y times the probability x2 less than or equal to y, and so on, probability xn less than or equal to y. Right. So each of these is a cumulative distribution function. This is the cumulative distribution function of x1 evaluated at y. This is the cumulative distribution function of x2 evaluated at y, and so on. But all the cumulative distribution functions are the same because x1 up to xn are identically distributed. So that cumulative distribution function is denoted by fx. So therefore, what you have here is fx evaluated at y to the power n. Now we can get the density function of yn by taking the derivative of this thing with respect to simple y. Then we get this expression, right? The derivative will be n times fxy to the power n minus 1, and then you have to multiply by the derivative inside this function, that is fxy. So therefore, this is the general formula for the distribution of the uh, largest order statistic when you are taking a random sample of size n from a distribution with CDF fx and density CDF capital Fx and the density simple Fx. Okay, so those two are easy because we can write down the required event easily in terms of x1 and up to xn. We were able to write down it easily. Now let us look at the distribution of rth order statistic, where r can be anything from 1 to n integer values. Suppose x1 up to xn is a random sample of size n from a continuous cumulative distribution function fx. Let yr be the rth order statistic. Find the distribution of yr. So we will use the same technique, that is the cumulative distribution function technique. So cumulative distribution function of yr evaluated at simple y is equal to the probability yr less than or equal to simple y. That is the definition of the cumulative distribution function. Now, we want to write down that event yr less than or equal to simple y in terms of our x1 up to xn. Because we know the distribution of x1 up to xn, therefore we will be able to use that if we write down this event in terms of those x's. So yr less than or equal to simple y, right? Yr is the random variable, simple y is a given value, fixed value. So yr is less than or equal to simple y if and only if at least r of those x1 up to xn are less than or equal to simple y. Right? Yr will be less than or equal to y if and only if at least r of those x1 up to xn are less than or equal to y. Right? So that means, if, for example, if you consider the number of x's, right, capital X, capital X2, capital up to capital X, and now out of those, let's consider the number of x's which are less than or equal to simple y. Then probability yr less than or equal to simple y, that event is equivalent to the number of x's which are less than or equal to y is greater than or equal to r. At least r of those. So greater than or equal to r. Right. So in order to write down this thing and find out the distribution, let us define a new random variable, say zi is equal to 1 if xi is less than or equal to y. Right? We are interested in that x's are less than or equal to y. So z1 is 1 if x1 is less than or equal to y. Otherwise, z1 is 0. Z2 is equal to 1 if x2 is less than or equal to y. Otherwise, it is 0. Like that, we can define up to Zn. Zn is less than or equal to 1 if xn is less than or equal to y. Otherwise, it is 0. So you can see that each Zi is a Bernoulli random variable taking values 1 and 0 only. And what is the probability that Zi becomes 1? The probability that Zi is equal to 1 is the same as probability xi less than or equal to y. Right? The probability that xi less than or equal to y is the same as the cumulative distribution function CDF of xi evaluated at y. Right? So we can say that Zi is a Bernoulli random variable with probability of success, that is the probability that Zi is equal to 1, is equal to the cumulative distribution function of xi evaluated at y. Right? The cumulative distribution function is a probability always. So that is the probability of success in this case. Right. So if you now, here I mentioned that we are interested in the number of x's which are less than or equal to y, right? So how can we get the number of xi's which are less than or equal to y now in terms of z, right? Zi will be 1 if xi less than or equal to y, right? So if you add all those z1, z2, z3 up to zn, you get the number of ones, right? So that will give you the number of x's, capital X's, which are less than or equal to y. So therefore, this event, the probability that at least r of xi's are less than or equal to simple y, I can write down using these z's. So that is the same as the probability that sum of zi is greater than or equal to r. So this will be the same as the probability that sum of zi, I from 1 to n zi, that is a complete random variable, greater than or equal to r. Right. Now, each zi is Bernoulli with some p, where this p is equal to fxy, right? Because fx1y, fx2y, fx3y, all those are the same. Therefore, this p is equal to fxy. Right? So zi is, therefore, what is the distribution of this sum of zi? Because zi's are independent now. Right? Zi's are based on xi's are independent. So therefore, sum of zi is has a binomial distribution. I from 1 to n zi has a binomial distribution with n and this p here. This p, that is equal to this. So therefore, we know the distribution of this quantity, and therefore we can get an expression for this probability, sum of zi greater than or equal to r. So that's what I have done. I have right. So this is the explanation. Then sum of zi is a random variable which gives the number of xi's which are less than or equal to y. Since each zi is a Bernoulli random variable with probability of success theta or p, that according to what I wrote earlier, equal to fxy. Right. So then sum of zi has a binomial distribution with parameters n and this theta. Right. The same thing that I wrote as p earlier. So therefore, the cumulative distribution function of yr evaluated at simple y is equal to this probability. So that is equal to sum of j from r to n. We can get the binomial probability, right? Uh, ncj and then theta to the power j, 1 minus theta to the power n minus j. Right? Because we want this to be greater than or equal to r. Right. So this thing goes from these general values for this thing binomial is from 0 to n, but now we are looking at the probability that it is greater than or equal to r. Right. So therefore, we have to add the probabilities, binomial probabilities from r to n. Right. So this part is the probability that is sum of zi is equal to j, and j has to be change from R to N and add them up to get the total probability. Right. So this is the first expression that we can get. We can see that this is in terms of the CDF of X. But of course, we can get a better expression than this, especially for the density function. If I want to get the density function, I have to take the derivative of this function. Right. Notice here we have to get the derivative with respect to y. Here this involves a summation first of all, and then a product of terms. product of functions of y. This is a function of y. This is also a function of y. Therefore, we have to apply the product rule when you're taking the derivative. So that will give you this expression here, this thing plus this thing, right? So keep the first, take the derivative of the first term and then keep the second one first fixed. And then when you're taking the derivative of this first term, you get this term. And then keep the first term fixed and then take the derivative of the second term. And then when you're taking the derivative with second term, you get this one, right? So that is the first step. And then what is done here is separate the first item coming from this summation here, j equal to r summation, right? So that is this term here. And then the remaining terms, j from r plus 1 to n, this term is this one. And this negative term is this one, right? Now, if you make a substitution, like k is equal to j minus 1, then I can write down this expression in terms of k, right? I will write down that expression in terms of k, then you get this expression here. And then you have this last expression coming from here with this minus sign, right? But if you now look at this term and this term, you will see that these are the same, right? These two are the same. Right. Only difference here is here I am adding over k, here adding over j. That is the only difference, but the summation is the same. Therefore, these two will cancel out. The final result will be this expression. Therefore, the density function of the rth order statistic evaluated at y can be obtained using this expression here. R times NCR fxy to the power r minus 1, 1 minus fxy to the power n minus r times the density function of x evaluated at y. So that is the general formula, right? So if you put r equal to 1, you will get the previous formula that we got for the distribution of the minimum. And if you put r equal to n, you will get the distribution of the maximum. Right. Okay. So now let's look at an example. Let's find out the rth order statistic, the distribution of the rth order statistic when we consider a random sample of size n from a uniform distribution in 0, 1 interval. That is the standard uniform, right? So x1 up to xn all are IID uniform 0, 1. YR is the rth order statistic. So let's directly apply to the formula. So in that case, the density function is 1, right? Of any x, the density function is equal to 1. The CDF evaluated at y is equal to y. You can easily derive those expressions. Therefore, when we apply into the formula, we get this expression here, right? So this will be just y and 1 minus y, and this is just 1, right? So this is the expression that you get. And actually, this is the density function of a beta distribution, right? Beta distribution. So rth order statistic has a beta distribution with first shape parameter equal to r, the second shape parameter equal to n minus r plus 1, right? So we saw actually when we were deriving the third order statistic, for example, right? All of them are generally beta distributions because beta distribution is a family. That family has large number of shapes, right? So that exponential distribution is also a kind of a member, right? The distribution that we got for x1 was exponential. So that is actually a particular member of this one. We get that one when r is equal to 1. And also we saw that the distribution of xn is negatively skewed. So it was almost like the mirror image of the distribution of x1. Right? That distribution is also beta distribution. We can get that one when r is equal to n. Right? And then we also looked at the third order statistic. For example, r is equal to 3. In that case, we had something like unimodal distribution, and it was According to this theorem, it is also should be a beta distribution with R equal to 3 and n minus 3 plus 1, that is n minus 2 distribution, right? So we could have checked that one also by drawing the actual beta distribution on top of that. But in that case, we had only 1,000 values. A better histogram would have been obtained by about 10,000, using about 10,000 values. Then, of course, we could have superimposed the actual density theoretical one on top of the density histogram, and they would have been very close, right? Now let us one more example. Here we are going to look at the distribution of the median, because median is an important quantity, right? Important statistic. So, of course, median, here we are talking about the sample median, right? When you have n observations, we want to consider the sample median and we want to look at the distribution. So to make it easy, let us assume that n is an odd number, right? N is an odd number. Then here I'm taking this example from the book. In the book, it is considering the Laplace distribution. Data are coming from the Laplace distribution with some location parameter mu and rate parameter lambda. And n is odd, right? So in that case, the R value is actually n plus 1 over 2, right? The position of the median is n plus 1 over 2. That will be our R. So that R is the order of our order statistic. We want n plus 1 over 2th order statistic. So therefore, we want the distribution of x within bracket R here. So let's call it M, right? And from the theory, we can find out the cumulative distribution function of the Laplace distribution to be this thing, right? We have discussed about the Laplace distribution earlier in one video, and we can find out always the expressions for the CDF. And it has two parts like this, right? The cumulative distribution function of the Laplace distribution, when x less than mu is given by this expression, when x greater than mu, it's given by this expression. So if I want to get the cumulative distribution function of this M evaluated at some value, simple x, for example, then I can directly apply the method probability M less than or equal to simple x, and that will be given by this expression, right? So if I substitute now, the question actually asking find the CDF, right? So here I'm just finding the CDF. Right? So I can derive depending on the value of x, I'm calculating this fmx, right? I have to get the correct expression from these two expressions. For example, if I'm considering a x value less than mu, in that case, fmx here, I have to substitute this expression for this, and here also the same expression. Then I can get the expression for the cumulative distribution function of the median at that value of x. If I'm considering x value which is greater than mu, at that value, I'll have to substitute this expression for fx here and here. Then I will get the cumulative distribution function of the median at that value of x. So that's how you get the cumulative distribution function. Depending on x, using this, you can derive it. So I have actually drawn the cumulative distribution function of the median when the data are coming from a Laplace distribution with mu equal to 0 and lambda equal to 1. And I'm considering sample size 5, right? So when x values are less than 0, in this case, I have to use this formula here with corresponding lambda and mu for the cumulative distribution function here. When I'm calculating CDF at any value in this region greater than 0, then I'll have to substitute this expression for fx and fx here. So doing that, I got this CDF. Right. So that is the CDF of the median of a sample of size 5. Right. So that is the end of this part, which concludes our discussion about order statistics. So I think that is a good place to stop this video. In the next lecture, I will discuss distributions of transformations, how to get the distribution of a transformation, one-to-one transformation. Say, for example, x is transformed into y using some function g, where g is a one-to-one function. First, we will consider that. We will derive a formula to get that thing. And then we will look at some examples. And then we will extend that to find out the joint distribution of a transformation of uh, a pair of random variables. Suppose x1 and x2 is a pair of random variables with some joint distribution. And suppose we transform that x1, x2 into y1, y2. And then how do you find out the joint distribution of y1, y2? That will also be discussed. So that will be an extension of this one, right? So those will be discussed in the next video. That will be actually next week.